In this problem, we'll assume we have a 70-kilogram student. He's standing still, not moving, on the ground of the Purdue campus, and it's at this latitude. And normally we would say this is the free body diagram of this person. He's just standing still, he's not moving, he's on the surface of the earth, he's got a force, gravitational force pulling to the center of the earth, he's got a normal force holding back up, he's got no forces in the x direction. We'll assume there's no wind blowing on him, there's no other forces acting on him to pull him one way or the other. So that's it. And so we say there's no net force on him, because these would be the same magnitude. There's no reason for him to accelerate, no change of velocity, and this would be the end of the story. But what I want you to do in this problem is that we'll see what assumptions we're making for this student standing on the Purdue campus. And there's two things I want you to consider. First, let's include the rotational effect of the Earth. So we'll assume the Earth is a perfect sphere and it's of this radius, and let's see how that changes the problem. And the second, let's assume that his body is water, which we'll assume is 1,000 kilograms per meter squared, and he's standing in air. So we'll assume he's in air, and air has this density. So those are the two things I want you to include now. We'll include the Earth is rotating, and we'll include that there's some buoyancy effect. And we'll see how this free diagram and how the forces change as a result of those two assumptions. And to see if in normal problems is that good just to neglect those things. So two questions. First, what's the magnitude of the direction of the net force on the student, with including these two effects? And number two, determine the magnitude and the direction of all the forces acting on the student. So pause the video right now, and now consider the Earth was rotating. And let's consider the buoyancy effect of the student, and see how that changes the net forces on the student. For most physics problems on the Earth, we generally assume that the coordinate system that we're going to have is rigidly attached to the surface of Earth, and that's introduces a very small error for most problems. For example, a ball flying through the air, or car driving, or some collision of two particles. In this problem, I've asked you not to make that assumption, and that assumption of this coordinate system not being fixed to Earth would only show up probably in real practical problems, like an artillery shell traveling north to south, 50 miles or something like that, where would be a significant error, you'd miss the target. So that will continue to be the common thing we'll do. We'll say this coordinate system is rigidly attached to the surface of the Earth, but this problem's not asking that, it's asking for something different. We'll talk about that. In reality, you see, if we attach our coordinate system to the surface of the Earth, for example at Purdue University, as the Earth is rotating, that coordinate system is accelerating. It's because there's a rotational component to it. So a better inertial coordinate system would be, for everything rotational, we say would be the axis of the center of the Earth. So if we had a coordinate system along the center of the Earth, and at a moment of time a radial projection through that point, that would be an inertial system which would not have this acceleration component as this non-inertial coordinate system has. So that's the coordinate system we're going to pick for this problem. We're going to pick a coordinate system that's not rigidly attached to the surface of the Earth and is accelerating, like this one is, about the center. We'll pick one which is to the center of the axis of the Earth. In this problem, we're going to pick this system as a student, surrounding everything else. And before we actually start solving a problem, I just want to get a vision of the Earth and kind of the coordinate system and what's kind of happening. So if we look at the side view of the Earth, so this is the equator, the surface of the Earth, and this would be the latitude of the Purdue campus at this degree. And so from the side view, this sphere is just rotating about this central axis of the Earth, and it's rotating at a constant velocity. And then from the top view, then if I get this plane that's rotating, if I just look at it from the top view, it's just we're assuming it's a pure circle. And so, and we'll pick at this instant of time that we're going to look at. The student here is in this orientation, and he's revolving around the circle at that moment of time. He's right there, and he's moving to the right here at this velocity. And we won't pick the coordinate system to be the surface of the Earth. We'll pick the coordinate system to be to the central axis. So there's a central axis of the Earth, and from the instantaneous position where this person is right now, we'll call the r direction from the center of the Earth to that person. We'll call theta here, this perpendicular direction, that we'll call z along the axis. And you could call it r, instead of r, you could call it perpendicular. This would be parallel to motion, and z, you can pick your whatever you want to call them, but that's what it's going to be. And so we're going to have essentially it's good. This person is just rotating along this circle perpendicular to the central axis at that elevation. And so one question is, what's the radius at that position? Well, the radius is just from trig, the radius of the Earth times the cosine of the latitude. We also know that this is rotating at constant speed. It's the Earth spinning at, we'll assume, it's constant speed, which is very good approximation. And so what's that rotation? What's that angular frequency, rotational frequency, whatever you want to call omega? So the omega is 2 pi radians per revolution, and the question is how long it take for a revolution. It's 24 hours. So if I do the conversions here to radians per second, I would get this many radians per second. So very, very slow relative to most problems we're thinking about as far as how many radians per second it goes. And then what's from this from omega here, the angular frequency, I can get my velocity in the theta direction. So the velocity is just omega times r. Here's omega. I won't use this number. I'll use the true numbers here. Do the math. Do my unit conversion from kilometers to meters. So turns out when you're standing still relative to the surface of the Earth at this position, this latitude, you are going relative to the coordinate system of the center of the Earth, you're going at 353 meters per second, which is approximately 789 miles per hour is the velocity you're going here. And at this moment of time, well, essentially at every moment of time, you're not moving any change in the r direction. So my velocity in r direction is 0. So this kind of gives you a idea of the scale of the velocity you're going. For momentum problems, we're not so much worried often about velocity, but the change in velocity, change of momentum with time, which we're assuming the mass is going to be constant of this person. Well, so that would be change of momentum is mass times change in velocity. So change of velocity in this direction is 0. It's a constant. It's because we're assuming that omega is constant. There's no rotational acceleration. However, there is a acceleration which is going to be towards the center. When I have any rotation going on, there's an acceleration. There's an acceleration towards the center of the part, which is described in, these are two equivalent forms of it, minus omega squared r, or minus v squared over r, where r is a constant value. So I'll pick this form of it and substitute in the values here and solve for it. So this is the, it's a minus. That's a big deal. So it's a minus. which means it's towards, since I define my coordinate system as here, the positive being in that positive direction, the acceleration radially is towards the center of, and that's what the minus signifies, and as of this magnitude. And you can see that this may give you a clue as to how important this is. If we think of g of 9.8 meters per second squared, kind of the ratio of this to g, it says how important that term is, considering that we're rotating. Now, starting to solve the problem, first of all identify, well, we choose this as our system, we'll choose the student as our system, and we'll assume him to be a particle on the surface of the world, so we're not going to assume that any rotation that he has about his center of mass is part of the issue. Surroundings, everything else, and then from initial to final time, we're going to assume that all the time the student standing still is part of this issue. So here's kind of a zoom up of the Earth, the student, and the Earth is spinning around, and this flat plane right here at this radius, as far as the student's concerned. So the student's just spinning around in a circle around the central axis of the Earth, and we had our coordinate system from the central axis of the Earth. We had a radial, we had a z, and then we had and you can call this. And into the board, we can call our theta or our parallel. So this would be perpendicular and parallel, could be another way to doing it. So now if we just zoom up on the student here standing on the surface, we'll draw all the forces acting on him. And we have the center of the Earth right is down here, so we vectorially sum the forces are going to go to the center of the Earth. And so that will be the mass times gravitational, that is downward. Then we have a buoyancy first, which is in that same directionality, but same vector direction, but this time it's going to be upward. And then we're going to have some force on the ground, and in this free body diagram I'm going to choose to say I'm going to have a normal force in this going against the center of Earth, and we don't know, there could be some frictional force acting on him. So I'll choose it this way. Another alternative to how I would have called that out, I could have had said that reaction force between the ground, that force acting on the ground and the student, I could have it in the r direction, or I could add a component in the z direction. We know that the student at this moment of time, he has a velocity which is into the board, because it's spinning, the Earth is spinning counterclockwise. So his velocity and momentum would be into the board. I also like to draw acceleration. We know he's just spinning around in this flat plane right here, so he has no acceleration in the z direction, going constant velocity, so he has no acceleration in the parallel or in the theta direction, but he does have an acceleration towards the center of rotation. So I'll typically draw that as like double arrow or something to signify that's not a force, that's an acceleration in the r direction. And we know spinning at that constant velocity around, or the omega we found before, so that we know that the magnitude of the acceleration is pointing inwardly, so it's very important to remember that minus. And these are either one of these is an equivalent way of determining that acceleration. And often it's accelerations, since we're gonna do acceleration or the change in velocity, which is the equivalent thing, it's often very convenient to have my coordinate system often set up so that I have my accelerations line up with one of those, because I know this acceleration in the r direction, and I know he's not going up and down in the z direction, so my acceleration in the z direction is 0, which is also my change in velocity or change in momentum. So he has a change in momentum in the r direction, he has no change in momentum in the z direction. So this was one way I could have done it. I'm going to use this way, and now you can pause the video and let's write the change in momentum equations for the R and the Z direction.